So we're continuing with section 3.10, and these are related rates. We're looking for rate of change for one quantity when rate of change for another quantity is given. And so this question is asking the height of a cylinder. This is a cylinder, and then the height is increasing if we call this h. dh dt is equal to 6 meters per second. And then the radius is decreasing. This is the radius r. dr dt is decreasing by 3 meters per second. And then it's asking how fast is the volume of the cylinder changing when the cylinder is 5 meters high and has radius of 6 meters. So at that instant, h is equal to 6 and r is equal to 5. So how do we do this? First of all, I have to, I'm looking for the change in volume. So I'm really looking for dV dt. What are the parameters that I know, and I have the rate of change, and they are h, r, and I want to know v. So I have to relate these quantities together. Let's see. V for the cylinder is pi r to power 2 times h. To relate these together, relate the rates together, I have to take the derivative of both sides. dV dt is equal to, let's remember, h is just a constant, so it's going to be the coefficient here. So I'm going to go pi, derivative of the first one, derivative of outside is 2r, but r is a function of t, so I have to write dr dt. Then times h, because this is a product rule. So that's this part is this part is the derivative of r squared, then times h. Now I have to do r squared times derivative of h. So pi r squared, derivative of h, which is dh dt. A little easier because h was not it was not a composition or a non-trivial composition function. It was just h. And so now that I set all these up, what is remaining is that to calculate dV dt, I have to plug in the values. I know r, and I know that's 5 at that instant. See, r is changing, but it's 5 at that instant. dr dt is -3. R squared is going to be 25. Oh, and h is 6. dh dt is going to be also 6. So now I can calculate the change, the instantaneous rate of change of volume over in time. So when you, now it's in a nicer way of writing, because typing is always neater and cleaner. This is the other way that we wrote it, and if you plug in all the values, over here is 6, over here is the r squared is radius of 6, that's 36. And then r over here is going to be again 6. And height is 5. And the change in radius is -3. Change in height we know it was 6. And so if I use that, then I can tell you that the answer is 36 pi cubic meter per second, which is this value. Here's another example, a very good example of how we can use the related rates. The question is, air is pumped into a spherical balloon at a constant rate of 3 cubic inches per second. So I have this pump and I know the rate that it pumps air. And then when the radius of the balloon is 5 inches, how fast is the surface area expanding? Can you guess why I need this? I'm giving you a hint. How fast the surface area is expanding is important when you know the balloon is going to pop. And so I can look at the radius of the balloon and have a guess and when it's going to be popping. And so this is interesting in that way, and we figure out how when we're supposed to stop or when we shouldn't pump anymore. And so let's see how this goes. What information do I have? I start with the sphere. So I have this sphere, and then I know that the air is being pumped. So dV dt, which is the volume, is 3 cubic inches per second. And then the radius is 5 inches. Now it's asking me to find what? I find the dA dt, that's the change in surface area. And so, well, I know how volume is related to radius. Let's start with that. And so I write volume of the sphere is 4 pi r to the third over 3. Okay, so that's one thing. Then I know that the surface area is related to r with 4 pi r squared. Now, how do I use this piece of information? Let's try to take derivative of the implicit differentiation of both. So I'm taking the derivative of the first one, and I'm taking the derivative of the second one. First one is giving me the derivative of v with respect to t is equal to, here, 4 pi third is the constant coefficient, and then derivative of r to the third. So it would be 3r squared. So I have 4 pi third times 3r squared, which makes it 4 pi r squared, then derivative of inside, which is dr dt. Then I will have in here dA dt, which is this time, and the 2 comes down, and I get 8 pi r dr dt. Now, so the question is, what do I know? What do I need to find? I know this value is equal to 3. I know that value is equal to 5. I don't know this. This one is the one that the question is asking. This one is something that I know. But here, in the first equation, this is the first equation, I only have one unknown, dr dt. In the second equations, I have two unknown, this one. This is the second one. dr dt and dA dt. But I can solve dr dt in the first one and then plug it into the second one. And that's what I do. So I solve dr dt in the first one. dr dt is equal to 3 divided by this whole entire thing. 4 pi times 25, which is 100 pi, right? And then I plug that back into here, and then I solve for dA dt equal to 8 pi times 5, which is going to be 40, and times 3, which is 120, and then divided by 100 pi, which is 12 pi divided by 10 pi. Pi simplifies, and we get 1.2. And this, what is the unit for this? The unit for this is inch squared divided by second. And this one was inch per second. Another question that is very helpful. Let's say you're filming it